Okay, class, Master of Science students. Uh, as you can see, what you put on the board, I believe it can be seen, or maybe let me put it slightly like this one. It's showing that the magnitude of the gradient, which you call the rho, is important. Yeah. So there are a number of reactions which are put on the board, which will try to give you a clarification on that. Uh, Now, want to take this standard uh, hydrolysis of or the ionization of the carboxylic acid in water to form the carboxylate plus the protonated water. In this case, if it is benzoic acid, then okay, if you're just going to have various substituents, for this reaction, the raw value is 1, yeah? This is just the standard gradient of 1. What has been seen is that if you're going to use that one as the reference figure to see how other reactions are going to be either have more or less, um, we had said that the raw value, before we look at the others, is an indication of what is happening to the transition state of the rate determining step? What is happening to the transition state of the rate determining step? In the rate determining step, what is happening is are the electrons going, are the electrons doing what? Going to the reaction center, or are they going out? In other words, are you having a developing negative charge, or are you having a developing positive charge? Okay, so from here to here, you can see that there is a developing negative charge. Yeah. So if that is the rate determining step, then the rho is going to be positive, and you're going to see for the hydrolysis, all the rho values are positive. That is to tell you that in the transition state of the rate determining step, there is a developing negative charge. Now there are two ways in which you can get a positive rho. One is that there is a developing negative charge, or there is something like, or in the transition state, there's a carbocation, and then there is a decrease in that positive charge, maybe from positive to 0, or maybe there's a decrease in the intensity of the positive charge. So in that case, you can say there is a developing negative charge. A developing negative charge, there can be something like it was neutral, it's becoming a negative charge, or it was something like it was positive and then it becoming neutral. Something which was a carbocation and then it becomes not a carbocation. It means that there was a negative charge which flowed into the transition state to cancel out the positive charge, and therefore you end up with a neutral species. Yeah. So that can help you come up with a proper mechanism. So let's get to this other ones, using this one as our reference figure. In this case, we can see you've got your your carbonyl group for the carboxylic acid attached directly to the benzene group. In other words, it means that any changes in the electron density of the Y, what it's doing, it will affect the carbonyl group, because the carbonyl group is attached directly to the aromatic system. So any changes in the electron density here will directly affect the carbonyl group here. Now, in these other reactions, what can you see? That this is the reaction center, whereby there, that is the hydrolysis, where the hydrolysis is taking place. This is where the hydrolysis is taking place. This is where the hydrolysis is taking place. Now, here you can see, relative to what we had initially, there is an extra carbonyl group. There is there's an extra CH2 group, alkyl group. Yeah. So it means that the reaction center is not attached directly to the aromatic group, and that has caused the gradient to drop by half. Yeah. And if you're going to increase what? If you're going to increase the alkyl group, you can see the raw value decreases significantly. Yeah, to about almost a fifth of what you had if the reaction center was attached directly. Now, if I'm going to compare uh, which reaction, this and that are the same, other than the fact that that in this one here, this are CH2, this are CH2, and then here what I've done is what is to remove one hydrogen and one hydrogen here. So there is a pi system. There's a pi system. Can you see that? There's a pi system here. So in this case, if there is a group attached here to the benzene ring, it can influence the reaction center through conjugation. So if I've got something like a CH3 here, or any negative charge can come here, it will go here like here. So this pi system helps transmit the charge to the reaction center. So if you're going to have a conjugated system, that even if it's going to be far away but it's conjugated, that will help transmit the negative charge to the reaction center. But if I've got an alkyl group, like in this case here, there is so this reaction center is almost independent of the benzene because it's fairly far away. Yeah? Okay. But the fact that it is positive, it means that in the transition state there is electron density which is going into the reaction center in the transition state of the rate determining step. Okay. So now you've seen all the raw values are positive. So it tells you that there's a developing negative charge, or there was initially a positive charge, but being that positive charge is being reduced by electron going into that positive charge to make it neutral. Yeah? So there are two ways in which you can get a positive raw. Okay, right. So let me go to the other reactions, and then we can see the raw values. So I'm just looking at this thing because these are occasionally these are the source of questions which can really come. It's really good for you to know uh, that you are just given a raw value and then you're told determine the mechanism. Is it an SN1? Is it an SN2? Is it an E1 or is it an E2? Can you imagine that information you can be able to determine by looking at the raw value? Can you see here? You'll be surprised, but that's what's going to happen in these reactions here. There is an alkyl halide. In this case, there is a bromide group here attached to a CH2 here, and then there's the benzene ring. Here there is there's just an extra alkyl group here. Yeah. What can you see? Other than the fact that you're getting this product and also this product. If you're given a product, you can do what? Uh, assuming you are not given the product, yeah, and this is now where you can be able to be given this reaction. You're not given the product, you're just given the reagents, and then you're given the raw value, and then you're told determine the product and also the mechanism. Okay. Now this is what you're going to do. You're going to look at the raw value. This raw value is negative. This raw value is positive. This a fairly small negative value. This even this one is a relatively small raw value. You're going to see in some reactions you can have a fairly large raw value. Excuse me. But what can you see here? That the raw value being negative, in this case negative 0.33, it is telling you in the transition state of the rate determining step, there is a developing positive charge. And then in this other case, the rho is positive. So it's telling you in the transition state of the rate determining step, there's a developing negative charge. So that tells you, based on that one, you need to come up with the mechanism. Assuming you are not given the product, that will tell you that if the rho is negative, then it's telling you there's a developing carbocation, and therefore that tells you that that the mechanism is not going to be something like an SN2. Yeah, if there was a if that this now we are going to say, I'm going to rule out the mechanism being what? Being SN2, because if the mechanism is SN2, like in this case, I have what? I've got the hydroxide attacking here, and then I've got an SN2 like that. Yeah, I'm just trying to give, but that's not the mechanism because of the figure here. It means that in the transition state of the rate determining step, what's going to happen is that electrons are going into the reaction center. So in this case, the rho would have been a positive. So you're going to say, hey, that's not going to be the mechanism. Are you seeing that? Because in this case, if the OH will be attacking here, it is bringing electrons. And therefore, in the transition state, there will be a developing negative charge. And if there is a developing negative charge in the transition state, in the rate determining step of the, in the transition state, the rate determining step of the rate determining step, in the transition state of the rate determining step, that will tell you that you're going to have a positive rho. But the fact that the rho is negative, that tells you, hey, the mechanism, that's not going to be the mechanism. That the rate determining step will now be an SN1. That the bromide group is going to leave, and therefore you're going to be left with a carbocation here, which will be stabilized by the aromatic ring. Are you seeing that? You're going to be left with an aromatic ring, which will be, excuse me, you're going to be left with a CH2 here, which will be stabilized by the benzene ring. Yeah. So this means that the groups which have got a positive sigma are going to decrease the rate because they are going to be withdrawing electrons, and you are having a developing positive charge. And the ones which are going to be donating electrons, like methoxy group, are going to increase the rate because they are going to be stabilizing that carbocation. So you're going to get a negative rho value. So that tells you that based on the rho value, that the mechanism is going to be SN1. So that in this case, that will be, so you're going to be getting a CH2 here, and then the bromide is going to leave. And then in the developing positive charge, then the OH is going to attack here to form the final product. That's how you're going to eliminate the SN2, and you're going to get up with the SN1 just from the gradient. You can be able to come up with the proper mechanism. Can you see that? Let's look at this other case here. Yeah. So you've got a what? You've got a positive rho value. You've got a positive rho value, and it's quite significant. Positive 2. That's a very large. That's a large gradient of positive 2. So that is telling you that even if you are going to have something like an SN2, assuming you had something like an SN2 on this one here, it means that if this CH2 was to be the reaction center, then if you're going to have an SN2, then that will not be affected by, it's not going to be affected by the what? By the benzene ring, and therefore I would have gotten a small what? A small rho value where you've got a reaction center which is going to be away from the benzene ring. So in that case, even if the rho value would have been a positive, I would have probably gotten a positive 0.2 a raw value of positive 0.2. But the fact that the raw value is positive and it is large, that tells you the reaction center is probably attached to the benzene ring. Can you see that? That the reaction center is probably attached to the benzene ring. So that tells you the mechanism. Assuming you're not given the the product, then you're going to say, hey, in this one here, I'm not going to get an SN2 reaction, because that would have given me a small raw value. What is actually happening is something like an E2 reaction. In this case, the etoxide is doing what? Is abstracting a proton, and therefore there's going to be the electrons are going to go to the carbon, which is attached directly to the aromatic ring. So there is a developing negative charge as a result of the electrons being abstracted, and then the electrons which are coming in are going to be attached directly to the benzene ring. So any group attached to the aromatic ring are going to either stabilize or destabilize that developing anion. And the fact that the rho is positive, that tells you that electron withdrawing groups like the nitro groups are going to increase the rate, because they are going to be withdrawing electrons, and they will help stabilize that developing negative charge. But if you've got a group such as a methoxy group and the rest, the rate will be low. So the rate will be low. So they are going to do what? They are going to uh, destabilize the developing negative charge by causing a repulsion with the developing negative charge. So in this case, the mechanism is going to be what? Is going to be E2, so that in this case the hydrogen is going to come off, and then this other side, the the iodide is going to leave, and you're going to be left with a double bond. All that information you can only get from the raw value. So you can be given a reagent here, you can be given this one, and you can given here, and then you say determine the mechanism based on the raw value, and also predict the product that's going to be formed. Can you see that? You're just given the starting material plus the raw values, and then all that information you can actually get. Wow, can you see that? Very important information based on the raw value. The raw value gives a lot of information about the mechanism of what is happening to the transition state of the rate determining step. Now, okay, let us look at a number of reactions here. I think let me just try to see whether I can put the board like this. Excuse me, so that we can focus on this these reactions here. So there is an amino group. Can you see? Oh, it's not seen very well. So there is an amino group, and it's actually attacking a what? An acid chloride to form an amide. Yeah. So in this case, it's telling you what is if this the reaction center, what is happening? You've got electrons, and then in the rate determining step, that the electrons are actually going away from the reaction center. So there is a developing what? There's a developing positive charge. Or when you're going to have when you've got such a reaction, you're going to see that that the rho is going to be negative. Yeah, it's going to be what? It's going to be negative, because the electrons are flowing away from the reaction center. This is the reaction center, and it is attached to the negative ring. That tells you that excuse me. Yeah. So when you're going to have a reaction center attached to the benzene ring, then the raw value is going to be large. It can be positive, it can be negative. The raw value is going to be large. It's going to be more than one, probably a value of 2 and above. So that tells you, assuming you are given these reactions, and then you are to correlate to these graphs here, you'll be able to point to to the proper what do you call uh, the proper graph here. So there is a developing. Okay, so what's happening? Excuse me. What is happening is that if the amino group is going to be attacking, eventually it will end up with a tertiary carbocation. You can be able to come up with that mechanism in which the NH2 is going to have four groups, two hydrogens, this bond, and then the other bond, it will be attached to the carbonyl group and then the oxygen. So the nitrogen is going to have a positive charge, and because it is next to the benzene ring, it's going to be destabilized by any electron withdrawing groups. So you're going to see that plot is going to have a very sharp negative rho value. Looking at this other reaction number B, yeah, let's look at what's going to be happening. In the rate determining step, there's a what? There's that negative charge. It is attacking the ethyl group, and then there is a displacement of the iodide. So once again, you had a negative charge. Eventually, you will end up it being neutral. So the negative charge is vanishing. So in this case, you're going to get a what? The rho will also be negative. Yeah. So in this case, you're going to see that that if you're going to have electron withdrawing groups, they're really not going to be they're not going to destabilize this phenoxy ion because it is a full negative charge. Yeah. So even if I'm going to have nitro groups, so they're not going to destabilize this group much. So you're going to see yeah, the gradient uh, will just be gentle. It will not be as sharp as in the first one. In this case, it will be negative, but not as great as the one for the first charge, whereby the first time whereby you're getting a full positive charge of the tertiary quaternary ammonium ion. Now, in the hydrolysis, like in this case, you can see that there's a developing negative charge. So the rho will be positive, but the fact that there's an alkyl group next to the benzene ring, then the gradient is going to be positive, but not very large. So you're going to see the C is going to be a gradient, but not very large. Yeah. Now the one for the D, it means that uh, let, let me put this group like there's a what? There's a carbonyl group, and then there is an O, and then there is an ethyl group. Yeah. So the rate determining step, it is the attack of the what? Of the hydroxide group onto the carbonyl group and opening up to form the what? To form the tetrahedral intermediate. So in the reaction state, there is a developing negative charge. So the rho is going to be positive. And because that negative charge is attached directly to the reaction center, then it's going to be really large and positive. So you're going to see like for D, the gradient is positive and it is large because there's a full developing negative charge, and because it is next to the reaction center, it's going to be stabilized or destabilized by any group attached to the benzene ring. I'm saying this because you can be given reactions here, and then you can be told their graphs here correlate these reactions to the plot there and see which row corresponds to whatever reaction there. Can you see that? Okay, so I think I will stop there. The next thing which I will mention are we'll now be focusing on the group which is going to be attached to the benzene ring, because what has been seen is that there are some groups that that can actually interfere with the electron donation, and therefore the activity is going to be far much greater than would have been expected because of those conjugation effects. So you're going to see there are some new sigma values which have been developed to try to compensate for those figures, and then we look at deviations from linear plots. All the plots we've looked at so far have been straight lines, either negative or positive. But you're going to see later that you can get you can get you can either get uh, not a linear plot, but something like it's coming top and then moving down, or maybe it's moving down and then it's moving up. It gives a lot of information than this linear plots. That one you're going to see in the next presentation. So I think you've really I believe you've now enjoyed this session on understanding mechanism by looking at Hammett equations. Okay. Okay. So let me stop there.